All right, so in the last video, we covered end behavior of higher degree polynomials. And today, in this video, we're going to take a look at the real zeros of higher degree polynomials and using those two pieces of information to graph these polynomials. Okay, so basically, and you don't have to copy this down right now, but this is what we're getting at. So if we're trying to get to the point where we're graphing these, and if we know the end behavior, like let's suppose that as x goes towards negative infinity, we get negative results, and as x goes towards positive infinity, we get positive results. So we know the end behavior. Okay, so but then that's all we know so far. So once we start to find the zeros, which is essentially the same as the solutions to the polynomial, which are the x-intercepts, then what happens is if we know those zeros, let's suppose we have one there, we have one here, and we have one here. If we know these two pieces of information, we know the end behaviors and we also know the zeros, then we can come up with the basic shape of the graph. So I'm going to put those two pieces of information together, and from that I can see that my graph does something like this, where on the right hand side it goes towards positive infinity, and on the left hand side it goes down towards negative infinity. Okay, so that's why it becomes important that we learn how to find the end behavior and also the zeros. Okay, so let's begin. 3.2. And this is part 2. And we're still on higher degree polynomials. Okay, so we are going to be talking about the real zeros. So we are going to be a little technical here. And again, these are essentially the x-intercepts that we need in order to graph. Okay, so let's begin here. If p is a polynomial, and c, that's the letter c, okay, is a real number, the following are equivalent. And I'm just going to write TFAE. That's what we actually use in mathematics. Yes, way before texting started, we were using these. Okay, so the following are equivalent. So number 1, C is what we call a zero. C is a zero of P of X. So that's the equivalent of saying that X equals C is a solution of the equation P of X equals 0. And that's the same as saying that X minus C is a factor of P of X. And that's all the same as saying C is an x-intercept of P of X. Okay, so that's what we mean by saying that the following are equivalent. So if you know that C is a 0, then you also know that C is all of these other things. Okay, so if you know that C is a 0, then you also know that C is an x-intercept. If you know that x equals C is a solution, then you know that C is an intercept. Okay, so if x minus C is a factor, then you know that C is an x-intercept. Okay, so let's take a look at this example here. Suppose that I have this polynomial, p of x equals x minus 2 times x plus 3. So we have it in factored form, so the question here is, well, what else do we know? Well, according to these four things, well, if I have this polynomial, well, let's go through each one of these one by one. Okay, so if that's my factored form of my polynomial, then I know that x equals 2 and x equals negative 3 are zeros. Okay, so 2 and negative 3 are zeros of the polynomial. Okay, the second one, x equals c, is a solution. So the way we write that, x equals 2 and x equals negative 3 are solutions of p of x equals 0. All right, number 3, x minus c is a factor. Okay, and it's already in factored form. So, and we can already see that x minus 2 and x plus 3 are factors of p of x. And from all of this, we also know that c, which is 2 and negative 3. So we know that 2 and negative 3 are x-intercepts of p of x. Okay, so when we have any of those things, any of the four things, then we know the other three. Okay, so that's an example of when you're given a polynomial that's in factored form. Let's take a look at a graph, and let's see what we can say about all of those things if we are given this particular graph. All right, suppose that suppose that I have a point right over here and another one over here and one over here. Okay, and suppose that my graph does something like this. Okay, all right, so looking at the graph, what do we know? Okay, well, we see these 3 points, so we know that negative 1, 1, and 3 are x-intercepts, right? So we're going to go through each one of these again. Okay, and if we take a look, so this is what we can tell from the graph. So let's go ahead and begin with that one. So the intercepts are negative 1, 1, and 3 are x-intercepts. I'll call this p of x. Okay, and if that's the case, let's go ahead and look at them again. Since we can see number 3 right above here, the factors. So if these are the intercepts, so starting with negative 1, if x equals negative 1 is an intercept, then what would be a factor? So hopefully you see that it would be x plus 1. And then the next one would be x minus 1. And the third one would be x minus 3. Okay, so we see that these here would be factors. So if we know that these are the x-intercepts, then they came from these factors. So they would have to be the opposite, right? So that's minus 1. So we have the factor plus 1. That's positive 1. So we have x minus 1. That's positive 3. So we have x minus 3. Okay, so these are factors of p of x. Okay, and let's see what else is up there. Okay, x equals 2, x equals negative, the solution. So the solutions are the same as the intercepts. So we can say x equals negative 1, x equals 1, x equals 3 are solutions of p of x equals 0. Okay. And so the zeros, again, the zeros, the solutions, and the x-intercepts are all the same thing, right? So we can say negative 1, 1, 3, negative 1, 1, 3 are zeros of p of x. Okay. And what we're going to be doing in the following sections is focusing on solving higher degree polynomials. So you'll be seeing the question, find all the real zeros of the following polynomial. Find the zeros, find the zeros. Okay, so you're basically just solving, setting it equal to 0 and solve. Okay, now so let's go ahead and take a look at graphing. Graphing higher degree polynomials. Okay, so again, we need to know end behavior, and we need to know the zeros, which are the same thing as saying the x-intercepts. Okay, so if we can figure out those two things, then we should be able to get the basic sketch of the graph. All right, let's take a look at this example here. Let's go ahead and graph p of x equals x times x squared minus 4. Okay, so this form of the polynomial is not in expanded form where it's multiplied all out, and it's also not in completely factored form. So the way it's written right now isn't going to help us. Okay, so what we need are both of those forms that I just mentioned. We need it to be multiplied out completely, and we need it to be factored out completely. Okay, so we need it to be multiplied out completely, in which case here we get x cubed minus 4x. So we need it like this so that we can identify the leading term right here so that we can figure out the end behavior. Okay, so we're going to use this. Use this for end behavior. When it's written like this, however, it's very difficult to figure out the x-intercepts. So to find the x-intercepts or the zeros, we like it to be in completely factored form. So up here, this is almost what we want. Okay, so I'm going to ignore the x cubed minus 4x. I'm going to start from that original polynomial, and And I'm going to go ahead and finish factoring it. So I'll keep that x here. And I'll notice that x squared minus 4 is the difference of two squares. So that's going to factor out to x plus 2, x minus 2. So here, now that it's completely factored, I can use this for the x-intercepts. Okay. All right. So let's begin. So let's start with the end behavior. So again, end behavior, we're using this one over here. Okay. So again, we only need that leading term. Okay. So as x goes towards positive infinity. Okay. So it gets very, very positive, like 1 million. When I plug 1 million into that leading term, do I get a negative result or do I get a positive result? Hopefully you said positive. Okay. So on the right-hand side, that means it will be going up or down. Which one? On the right-hand side, it will be going up. Okay. Let's do the left-hand behavior. So as x goes towards negative infinity, so if I plug in a negative number, negative 1 million, into that leading term x cubed, I end up with a negative or a positive. Hopefully you said negative. Okay, so that means on the left-hand side, our graph will be going down. Okay. All right, so we know the end behavior. And let's get our zeros, our x-intercepts. So since we have it in factored form, this is the one we are going to be using. So we have x equals 0. We have x equals negative 2. And we have x equals positive 2. So that's where we're going to have x-intercepts. Okay, so when I graph this, I know enough information to get the basic behavior of this polynomial. Okay, so on the right-hand side, it should go up. On the left-hand side, it should be going down. I have an x-intercept at 0. I have one at negative 2. And I have one at positive 2. Okay. So the only way I can draw this graph so that my graph goes through these 3 points and ends up going up on the right-hand side and down on the left-hand side, the only way I can do that is by doing this. Okay, right here I'm turning. Where you turn, I'm not going to hold you responsible for knowing when to turn. So maybe right here, so maybe your graph looks like this. Maybe some of yours will look more like this. Okay, so how high you go or how low you go, the only way right now for you guys to know when to turn is by plugging in several values and plotting several points right around that area. But once you get to the next class, once you get into Calculus 1, then you'll be using calculus to figure out exactly. And it's not time consuming at all. Okay, so I'm not going to expect you to keep plotting points till you know when to start turning. Okay. All right, so let's take that off. Okay, so this follows exactly everything that I know about the polynomial. I know it's left-hand behavior, and it is going down. The right-hand behavior, it is going up. Okay, and my graph does cross through all three x-intercepts. Okay, all right, let's try another one. Okay, suppose that I have this polynomial. P of x equals negative x to the fifth plus 5x cubed minus 4x. Okay, so this is all multiplied out. Nothing is left, right? So this form right here is good to use for end behavior when it's all multiplied out like this. Unlike the previous example, it was not all multiplied out. Okay, so we're going to use this one for end behavior. We need completely factored form for the x-intercepts. So I'm going to factor this. I'm going to start with factoring out a negative x because they all have negative x in common. Okay, so I will have x to the fourth minus 5x squared plus 4. Okay, and then here I have, inside the parentheses, I have what's called quadratic in form. We looked at that. Okay, so I'm going to treat this like a quadratic and use my factoring skills here. So what times what is x to the fourth? So you should be thinking x squared times x squared. Okay, and we want to make positive 4 here, but then eventually get a negative 5. So the signs have to be the same to make positive 4. So the question is, will the signs both be positive or will they both be negative? So hopefully you said both be negative. Okay, and we can choose to make 4 by doing 2 times 2 or 1 times 4. So hopefully you're going with 1 times 4. Okay, so we are not factored completely just yet because here we have perfect squares. And same with the other one. We also have perfect squares, difference of perfect squares. So both of those are going to factor out. So the first one, x squared minus 1, factors out to x plus 1, x minus 1. And the other one, x squared minus 4, will factor out to x plus 2, x minus 2. Okay, so now this is completely factored. So we're going to use this for the x-intercepts. All right. Since it's right there, let's go ahead and write them down. Our zeros, or our x-intercepts. All right, so we're going to have one starting with this one. Okay, right over there. This one counts. So we have one at x equals 0. Okay, and then over here, the next factor, I get x equals negative 1. Okay, the next one, I get x equals positive 1. The next factor, I get x equals negative 2. And the last one, I get x equals positive 2. Okay, so I have a lot of x-intercepts. 1, 2, 3, 4, 5. One thing you'll know is that if this is degree 5, you will have no more than 5 zeros. Okay. All right, let's do our end behavior. Let's do our right-hand behavior. So as x goes towards positive infinity. Let's have a look. All right, so positive infinity, when I plug into that leading term there, I end up with negative. So p of x goes towards negative infinity. So on the right-hand side, my graph should be going down. Okay, the left-hand behavior. So left-hand behavior, that says x goes towards negative infinity. Okay, so if I plug in negative infinity to that leading term, I end up with positive. Okay, so on the left-hand side, our graph should be going upward. Okay, all right, so with these 3 lines of information here, I should be able to draw the graph of this degree 5 polynomial. Do you see how we are getting into more complex polynomials instead of just the quadratic, the parabola? Okay, so right-hand behavior will be going down, left-hand behavior should be going up. I have intercepts at 0. And I have one at -1, +1, -2, and +2. Okay, so my graph needs to cross through all of these points, and on the left-hand side, it should be up, and on the right-hand side, it should be going down. Okay, so one way to do it, okay, so we need to be going up on the left-hand side, go through it. Let me wait for it. Okay, and then turn around at some point to go through this next intercept. Go up and turn around at some point to go through the next intercept. Turn around to go through the next intercept. And turn around to go through the next one. And there are no more intercepts. And my graph should be going down according to my right-hand behavior over here. That says right-hand behavior should be going down towards negative infinity. Okay? So again, I'm not holding you responsible for knowing when to start turning to come back. Okay? You'll learn that in calculus. Okay, so notice that the graph did go through every single one of those intercepts. Okay, so this next example, I'm going to show you what happens when we have what are called double zeros. Okay, and what I mean by that is if you take a look up here, if we look at all of these zeros right on this line, they're all different, right? 0, -1, +1, -2, +2. None of them repeated. Okay, so when that happens, your graph goes through and then turns around and goes through the next intercept. Okay, when they repeat, something else happens with the graph. So let's take a look at this example. Okay, so again, this is written in a way where this form doesn't allow us to find the end behavior, and it also doesn't allow us to find the zeros. So let's go ahead and multiply this out. So we get -x to the 4th plus 4x squared. Okay, so this is the one we'll use for end behavior. Use for end behavior. We like it to be multiplied out completely so that we can see that leading term. right over here. Okay. So again, we only use a leading term for end behavior. Okay. And I'm going to skip that second line. I'm going to pretend it's there. I'm going to ignore it. I'm going back to the original way it is written. I'm going to continue from there and finish factoring it. I have difference of squares. So x squared minus 4 will factor out to x plus 2, x minus 2. Okay, and so here, this is the one I can use for my zeros, my x-intercepts. Okay, all right, so let's go ahead and list them. So notice this time, oops, I missed something. Yes, a square. There's a square right there. Okay, so notice here that another way to write this is like this. Okay, and so we see here that if I write down all the zeros, I have 4 of them. It's x equals 0, x equals 0 again, x equals -2, and x equals +2. Okay, so here, this time you can see that x equals 0 is a repeating 0. So that's where the graph becomes a little more interesting. Okay, so we're going to pay attention to what happens when you have repeated or double, what we call double zeros. Okay, so double zero, it's repeated twice. Okay, let's get our end behavior. So our right-hand behavior, so that's as x goes towards positive infinity. P of x goes towards, let's see, plugging in positive infinity, we end up with negative. So on the right hand side, it will be going down. Okay, so this is on the right. Our left hand behavior, so that's as x goes towards negative infinity. So if I plug in negative, I get a negative result. So on the left hand side, we are also going to be going downward. Okay, so let's go ahead and graph this. Pull this down a little so we can see the zeros. Okay, so right hand behavior is down, left hand behavior is also down. Okay, and we have a zero, a double zero right here. So I'm actually going to kind of highlight it. Okay, and you can do the same with your graphs so that you can keep track of where your repeating zeros are. And then we have one also at -2 and another one over here at +2. Okay, so here what happens is, okay, so our graph on the left hand side needs to be going downward. Okay, so I'm going to start like this, go through that single zero, and then I'm going to turn around at some point, and this time this next intercept over here, 0, since it's a double zero, I'm not going to go through it. I'm going to go towards it, and I'm going to touch it and turn back around. So that's what happens when you have a double zero. You don't go through it like you did over here at -2. You just, it becomes a turning point. Okay, so turn around. And this one is not a double zero, so I'm not going to turn at it. I am actually going to go through it. Okay, and we see that we hit all 3 intercepts, and our left-hand behavior and our right-hand behavior match what we were going to predict. Okay, so let's talk about double zeros a little more formally. So we're going to talk about double zeros and triple zeros. Okay, so if C is a double zero, or any even number, so if it repeats 4 times, then behavior at C is like a parabola. So again, if you have an intercept right here that is a double zero, then it's going to be a turning point. Okay. Or it could be going downwards. Okay. So if that's a double zero, then it would be a turning point, not a go through point. Okay. So let's take a look at a triple zero. If C is a triple zero or any odd number, so if it repeats 5 times, 7 times, then behavior at C is like x cubed. Okay. So what happens here is if you end up with an x-intercept that repeats 3 times, then if it repeats 3 times, this one here, then the graph behaves like x cubed. And it can also go the other direction too. Okay. And then it continues with the rest of its motion. Okay, so let's take a look where we have both a double zero and a triple zero. So suppose I have this polynomial p of x equals x minus 1 squared, x plus 2, quantity cubed. Okay, so it's already in completely factored form, so I can tell what the zeros are going to be. Okay, so here I can use this form for my zeros. If you want to write them out individually, you can as well. Okay, so you can use that one for your zeros, or if you want to use this one, that's fine. Okay, so, and then we'll come up with what we're going to use for our end behavior. Okay, so like right now, we can tell that our zeros are going to be x equals 1, which is a double zero. I'm missing one of these. And these guys are pluses. Let's fix all of that. Okay, there. Now that's all correct. So x equals 1. This is a double zero. and x equals -2. This one is a triple zero. Okay. Now for the end behavior, again, we don't actually need the entire polynomial multiplied out. We only want to know the leading term, so you can just take the leading term in each of these and multiply them together, and that's kind of easy. It's x to the 1, 2, 3, 4, fifth power. So not fourth power, fifth power. Where's the eraser? Okay. So that's 1, 2, 3, 4, 5 x to the fifth power, and plus dot, 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 but we don't need that. Okay. All right, so we don't need the rest of that. Oops. We don't need the rest of that for our end behavior. So let's go ahead and figure out our right-hand behavior. So as x goes towards positive infinity, p of x goes towards positive infinity. So on the right-hand side, it will be going up. Let's do left-hand behavior. So as x goes towards negative infinity, p of x goes towards negative infinity. So on the left-hand side, it will be going downward. Okay. So with, again, these three lines, I should be able to come up with the graph. Scroll. Okay. So at x equals 1, we have a 0. And this one is a double. I'll do this to kind of distinguish between that one and the other one. And x equals -2 over here is a triple zero. So this one, I'll go like this. Okay, and my left-hand behavior should be down. My right-hand behavior should be up. Okay, so this one is my triple. So here it's going to behave like x cubed. Okay, where's the rest of it? Okay, so it's going to behave like x cubed at this 0. And then eventually turn around at some point. And then over here, this one is a double 0. So over here, we're not going to go through this one. We are going to behave kind of like a parabola. Okay, so here we have much more interesting behavior. Okay, so that is pretty much it. So just be careful with your double zeros and your triple zeros. Again, these were double and triple zeros because you can see here x equals 1 repeated twice, x equals -2 repeated 3 times. Okay. All right, so if you have any questions, make sure you text message me or email me. And if you need to have an office hour through Zoom, let me know. Okay, enjoy the rest of your day.